Good morning, everyone. Today we're going to look at the topics from Section P. Um, the way I'm going to go about this is to really provide a couple examples. Make sure that you read the corresponding section and study any of the examples and work on whatever problems from the problem set you think would help you. One thing to pay attention to is the list of the conics and their general equations for their tangent and equation of a normal at a certain point. So this is going to combine a few things. Of course, we're going to be looking at parametrics, we're going to be looking at conics, and I'm even going to do an example involving locus, which of course is just a description based on a set of points that have certain conditions. So to start, let's take a look at this example. We are given a circle. We can write it in rectangular form as x squared plus y squared equals a squared, or we could write it in parametric form. X equals a cosine theta and y equals a sine theta. We know that with choices of a and theta, we would basically form a circle. We want to find the equation of the tangent and the normal. Now, everything is still going to be relative to the xy axis, but we can have the format in terms of either a or theta or a combination of those. So let's get started with this. When we see tangents and normals, we tend to think of calculus because we know that their slopes have something to do with the derivative. So let's find the derivative, or the dy dx. In order to do that, from parametrics, we first find dy d theta, and that of course is going to be negative a sine theta. Dy d theta would be a cosine theta. So dy dx would be just the quotient. The a's would cancel. We're going to get negative cosine over sine. Now I know that I could rewrite that, but I'm going to choose not to at this time. Now we can easily write the equation of the tangent. The equation of the tangent is going to be a general y value minus the specific y value, which is a sine theta. And that would be equal to the slope, which is negative cosine over sine, times x minus the general x, or the specific x value, which is a cosine theta. And now we just have to manipulate this to a certain extent. Maybe we just don't want any fractions, so we're going to multiply everything by sine theta. This would be y sine theta. This would be minus a sine squared theta. And basically here I'd have to distribute that negative cosine theta. So a negative x cosine theta. And then that would be plus a cosine squared. We see the sine squared, cosine squared. We can manipulate this. Move the x cosine to this side. We get x cosine theta plus y sine theta. And then we move the negative a sine squared to this side and factor out an a. We're basically going to have a. Because the sine squared plus cosine squared would of course be 1. So what we have now is an equation for the tangent line at a certain point in parametric form. So if we happen to know theta and we happen to know a in this format, we know the equation of the tangent. Now, likewise, we could come up with the equation of the normal. But when we do this, we would just have to take the reciprocal, and we'd end up with y equals a tangent theta of x, which we may already know. Okay, so part of the problem set will be to derive some of these formulas that are given, I think, on page 219, and pretty much just verifying these different formulas. Now, the next one is going to involve locus. So I want to give kind of an overview of this type of a problem, partly as a review of locus. What we have here is we have an ellipse. So if we have x squared over a squared plus y squared over b squared equals 1. We know that's the equation of the ellipse. And what I want to do is find the equation of the locus of the foot of the perpendicular from the center of the ellipse to any tangent. What does that mean? Well, this is it. Let's start with an ellipse. Okay, so here's the center. I'll call that center O for the origin. And we know that there's going to be a tangent, or I can draw a tangent. So I'm just going to put a tangent at some point. Now that point of tangency is a point on the ellipse, and on any ellipse we have A cosine, B sine. Those would be my parametrics for x and y. Of course, it's very similar to a circle, but these coefficients are different. That's what makes it different than a circle. Now, we're also going to look at any point Q on that ellipse. Or sorry, not on the ellipse, but at the foot of the perpendicular. So if I draw a perpendicular from O to the purple line, I'm going to call that point Q, and I'll just make this capital XY. I could make it about anything I'd like, but it's my specific point I want. Now, of course, at the endpoints of the minor axis, in this case, and the major axis, it would actually be on the ellipse. But other places it would not. There's the tangent, but they're not going to be perpendicular because it's not a circle. So now what we want to do is find the locus of all of those points. So if I continue to put all these purple tangents and find the foot of the perpendicular from the center to that tangent, what does that form? And that's really what a locus is. When we're asked to find locus, we're really asked to find an equation. Okay, so let's see what we got here. Let's start with the tangent at P. So the tangent at P and this is from that page 219. I don't want to develop it. I could go ahead and do the same thing I did here to develop this equation, but it's basically going to be B cosine theta x, get this, plus A sine theta y equals AB. That's going to be the equation of this tangent. And again, you could derive that, and that might even be one of the problems that you have to work on in the problem set or as an example. So now what we want to do is find the slope. The slope of this is going to end up being negative B cosine over A sine. Again, this is just some equation of a line. So OQ, slope, is of course going to be the reciprocal because we want it to be perpendicular. So A sine theta, B cosine theta. So that's what we have up to this point. So we're going to get a couple equations. One equation is going to be for OQ. The equation for OQ is simply going to be y equals that slope x. So that's one equation. Now, xy is on the tangent. This point xy is on that tangent, so the other equation could be this, that here's this equation, so we have B cosine theta, capital X, this should be small x, kind of looks big, plus A sine theta capital Y would equal AB. Now the next part is to somehow try to solve kind of this system of equations and put them into one. And the key is going to be working with this one first. I'm going to think of this, of course, as just y equals a over b tangent theta x. Sorry about that. Now from that, we get the tangent of theta. If we solve for that, would be by over ax. Well, we know then that we can sketch a triangle to fit this information. So if that's theta, the opposite is by. This is going to be ax. Of course, this is the hypotenuse. So from that, we now know that the sine of theta is going to be by over h, and the cosine of theta will be ax over h. So let's go ahead and use that over here. Okay, so this cosine theta would be ax over h. So we're going to have b times ax over h times x plus a times the sine of theta, which was by over h, times y equals ab. And again, this is going to be the capital X because it goes to that point. So these should be capital values. Should use subscripts probably. Now, if we look at this more closely, the whole thing becomes AB over h x squared plus AB over hy squared equals AB. Simplifying that a little bit, we can obviously take out the AB's, and we get x squared plus y squared equals basically h. But what is h? H is the square root of ax squared plus ay squared. Sorry, by squared. If we square both sides, we get x squared plus y squared equals, here I can take out, now I'll just keep it like that, ax squared plus by squared. Now initially these would be capital X and Y because that would be the specific point, but the locus is going to be all of those that fit this expression. So this would be the locus of all the feet of the perpendicular from the center of the ellipse to that tangent. Now, if you play around with, let's say, on Desmos, if you can use that, find that very easily, and play around with this, it's kind of neat because if A and B happen to be the same, you basically get in a circle, which hopefully you would see, that you could factor out that constant, divide by the x squared plus y squared, you basically get a circle. But as these things start to be different, you get some interesting looks. Sometimes it's almost like a track. Other times it's like a figure eight, but doesn't quite come together. So play around with that. So here's what we have. It's a neat combination of problems where you have to think of conics, first of all. You may have to deal with conics in terms of their parametric form. Of course, since we're dealing with tangents and normals, we're going to be finding derivatives. So it's a little review of that. Finding equations of lines, whether they're normals or tangents. And aside from kind of demonstrating or verifying that these different formulas hold, what we can do is even review some locus problems. So good luck with working through some of these problems. I know you currently have a worksheet that that kind of deals with some of the middle stuff from geometry. So get that to me whenever you'd like. And within a week or so, we'll have a test that I'll send and post, and we'll see how comfortable we are with this geometry. And then we'll think about moving on. So have a good day, and if you have any questions, please let me know.